Okay, everyone. So finally, the last lecture for Chapter 2. Now, what are some properties that are related to bonding? Okay, one would be melting temperature. Melting temperature right here. Now, why is this related to bonding? Well, it's all based on how stable that bond is. Or another thing we can think about is how much force is holding those two atoms together. Remember this graph over here? We said that nature's looking for a minimum, and that's where it finds this sort of happy place for how close these different ions or atoms are together. So what happens though is that as we increase the temperature of an object, these atoms are always vibrating back and forth, and they vibrate more and more. And eventually, what happens is we're in here to begin with, and they're vibrating back and forth. As we increase the temperature, they get more and more energy. They're vibrating further and further from each other, until eventually they bust apart. And when they get past this little hump, well, the bond breaks. They're no longer able to stay together. So what you can see here, though, is that the deeper this trough, so the lower the energy for that bond, then the harder it's going to be for that bond to break. The harder it is for them to be able to melt. Because they got to put more energy. They've got a lot further up to go. So the deeper this trough, this energy trough, the larger the melting temperature. Another thing would be the thermal expansion. And oh, fudge muffin. Well, I will fix this, but this is supposed to be an alpha. Okay. If you get to it before I get to it, you can get an extra credit point. But this will be around the coefficient of thermal expansion. So thermal expansion, you're like, okay. Well, once again, this is going to be connected to temperature. Last week we talked about melting point, but this time we're also going to be talking about the energy and how it is affecting the exact same thing. So the deeper our trough right here, the lower the energy of the state, the smaller its thermal expansion coefficient. Because once again, you see that this is really close together. Even when we increase the energy, increase the temperature, you see that they haven't moved that far apart. And this right here, those atomic bonds are how we get our thermal expansion. It is just that we have millions upon millions of them, which means that even if they're only stretching by like a nanometer, well, over a million of them, that is significant. That is significant. And the increase in the bond length, as it says, is just due to this asymmetry of this curve. So to increase the temperature, well, it gets further and further away, begins to expand further and further. So, I think that is everything. Oh, no, we got one more. I was off. So now let's look at the different materials that we've learned about so far: ceramics, metals, and polymers. Okay, ceramics, usually ionic. We have some covalent bonding if we're between things that have slightly similar, but those ionic bonds are pretty strong, those covalent bonds are pretty strong. Well, they have extremely high melting temperatures. They're very, very thermally resistive. They have very large energy troughs, and they have very, very small coefficients of thermal expansion, which is what you want. It's why we use them on the space shuttle. They can't be expanding like crazy. They can't be melting very quickly. Metallic bonding, not quite as strong. It's not quite as strong as the ionic bonds. And so they have, moderate everything. They're not the strongest bonds. They're not the weakest either. They have fairly high temperature, melting temperatures. They have a decent thermal expansion. And finally, covalent and secondary. And this is where it gets really weird, because when you look at plastics and things like that, like, well, those covalent bonds aren't that strong. But what you're actually seeing most times is the secondary bonding. That's between different chains of plastics. So they might melt very quickly. But that's only because the secondary bonding is responsible for most physical properties. It might also expand very quickly, but that's because the secondary bonding is responsible for that expansion at first. If you look at the individual chains, though, of plastics, those are very, very strong. That's why plastics don't break down for a very, very, very long time. So there's a lot going on in plastics, a lot going on in polymers. You have to make sure that you understand everything, and don't just take it at face value that, oh, this is weak bond, it'll break down easily. The bonds between individual chains, yes, but the chains themselves, not at all. Okay, so in summary, A material's chemical, electrical, thermal, optical are all determined by its electronic configuration. We learned that electrons try to fill up these electric shells, and they'll keep on going until they can finally fill them up. But if they don't have enough electrons, then they're going to start bonding because they want to either clean out one of their shells to leave it completely empty, or they want to completely fill a shell. We also learned that secondary, or what is called van der Waals bonds, are very, very weak. They're much weaker than the primary bonding types of ionic, covalent, and metallic. And finally, that the percent ionic character of a covalent ionic mixed bond depends on their electronegativities. The more the difference, the more ionic character. So that'll be all for today. I hope this helped you as we go through chapter 2, and we will be doing some problems in class. So have a wonderful day, and I'll see all of you next time. Bye-bye.